So, today we're going to talk about limits at infinity. Now, this is a different concept from infinite limits, where the result of the limit was infinite. In this particular case, we're trying to consider something that looks like this, where the x value that we are approaching is going to be infinity. And really all this means is that we're trying to say that as x gets larger and larger, f of x gets closer and closer to L. So we're trying to figure out what is the value that the function is attaining as x gets larger and larger, or we can also have an x approaches negative infinity type of setup, where x is going to get smaller and smaller. And again, when we use the word smaller and smaller, we're talking about more negative on a number line. So if you imagine these are the x values, you have 0, 1, 2. I want to know what is the y value of the function doing as x gets either larger and larger this way, or smaller and smaller that way. Let's consider an example of this so that we can see this in action. A classic example is to consider the limit as x approaches infinity of 1 over x. And we should be able to see that this is going to be equal to 0. And there's a couple ways we can do this. One is just to consider a table. If I consider various x values and I plug them in the function 1 over x, well, 1 over 1 is equal to 1, 1 over 10 is 1/10, and so on. So the idea is as x gets larger and larger, 1 over x gets closer and closer to 0. And the other way we can consider this is we can consider the graph of this function. You'll see that as the x values over here get larger and larger, we attain a horizontal asymptote. And we'll see that limits at infinity are, if they exist, will tend to the horizontal asymptotes of the graph. But you can see that this is going to get closer and closer to 0 as the x values get larger and larger. If we consider as x approaches negative infinity instead, we'll also notice that that's equal to 0 as well. And it will turn out that if the limit exists, that is to say, as long as this is equal to value, in most cases, the infinite and negative infinite limit are going to be the same. But there are some exceptions, and we will look at some of the exceptions later. So what are some of the basic results that we get when we consider limits at infinity? Things that are kind of like your basic toolboxes. We saw in the last example that 1 over x is going to tend to 0. But what about maybe things that are maybe just slightly more complicated, like if we put exponents here? Well, it turns out that for any value of n, as long as that n value is greater than 0, and again, we're just doing this because remember that if you take a negative of a negative, it's going to be positive. So really, we're going to assume if we've got positive n here and we take the limit as x approaches infinity, this will equal infinity. This should make sense because, if we have something and it's x to the n, that's a polynomial. This is just going to shoot up. It's going to get larger and larger. And then if it's 1 over x to the n, then it's going to be something that kind of works like 1 over x. Again, it might be a little bit steeper, but it's still going to be 0 in that particular case. Now, what about for negative infinity? Well, here we have to be a little bit careful. And we'll actually look at this, the other cases here. But for negative infinity, we're only going to consider n in z plus. So we're considering not just that n is some value, but n has to be a positive integer. And the reason why we do this is because of the issues with taking square roots of negative numbers, which we'll look at in a later video. So as long as we're dealing with positive integers, if we take the limit as x approaches negative infinity of f of x, we'll notice that this is going to be infinity as long as n is even, and negative infinity as long as n is odd. And really, this shouldn't be a surprising result. If we look at the following two graphs, if we have something that looks like x to the power of n and it's even, what you'll notice here is we've got this nice even symmetry here, and it's symmetrical at the y-axis, so it's going to go to positive infinity. Whereas if you have something like, so this is like y equals x squared, and then if you have something like y equals x cubed, and our integer is odd, then as it goes to negative infinity, you'll notice that this thing will decrease and go to negative infinity. Now, regardless of whether n is odd or even, the limit as 1 over x to the n as x approaches negative infinity is going to be equal to 0. So that won't change. So you can kind of fill in a graph that looks like this. It will have something like this. Okay. But as I said before, these have to be positive integers, or I guess negative integers will basically be this case. This is just for definition purposes, but we can't deal with limits at negative infinity as easily if we have something rational. So we will look at it in a later time, things like, what happens if it's, x to the, 1.5. And taking square roots of negative numbers, we'll see that this doesn't really work too well. But there are cases where it does, and we just have to be careful. So let's just do maybe one more complicated example, and we're going to find this limit by effectively using many of the rules that we did above. And there's actually a couple ways to the problem. In the next lesson, we'll look at a little bit of a shortcut, but the more direct way to deal with a problem like this is that we want to kind of simplify this in such a way that we have something that ultimately just has like a single x in it. And what we want to do in a situation like this is that we want to basically find the highest power of x that occurs among here, which is going to be x to the fifth. And then what we want to do is we actually want to divide every term out by 1 over x to the fifth. So we're going to do that right now. We're going to multiply this by 1 over x to the fifth in the denominator and also in the numerator, and we have to distribute that through. And we're going to see what happens here. So this is going to be, again, we want to make sure we have the limit as x approaches infinity here. This is going to become 20 x squared over x to the fifth minus 3x over x to the fifth. And then over here, we've got 3 x to the fifth over x to the fifth. So again, we're dividing every term by x to the fifth. And then what we're going to do is we're going to simplify these exponents as much as possible. So remember that if this is 2 minus 5, it's going to be x to the negative 3, but we can just write that as 20 over x cubed minus 3 over x to the fourth over, and then here we just have a 3. Here we have a minus, and then this will be 4 over x to the third, and then this will be 5 over x to the fifth. And now, with limit laws, we can effectively break this down and we can take the limit of each of these terms. So when we do that, this will become the limit as x approaches infinity of each of the terms. So this will be 20 over x cubed. And actually, we can even take the 20 out. So we'll bring the 20 out here, just so that we can have consistency with our limit laws. And this is a very common strategy to take in math, is to basically take a problem that's complicated and then turn it into something that looks a little bit more interesting. Again, this is a little bit of a cumbersome process to write out. And when you're actually doing problems like this, I would say that for the most part, it's unnecessary to do this. I'm just doing this to basically show that we can do this type of limit kind of from first principles. So anytime we've got something that's 1 over x to something, all of these limits are going to be 0. So this is going to be 0, that's going to be 0, this is going to be 0, that's going to be 0. So you'll have 20 times 0 minus 3 times 0. This is going to be 0. And then notice that we don't have a 0 on the bottom. We do have a real number, 3. So we can tell us that our answer here is going to be 0. So that's how we can at least primitively solve limits at infinity. Next time, we'll show that there are some shortcuts that can help us do these problems a little bit more efficiently, and we can connect it to how we would find horizontal asymptotes in a pre-calculus class. But that'll be left to next time. I hope you found this video useful, and as always, take care.